M2. So M1 is equal to 2 raised to power K1 and M2 is 2 raised to power K2. The combined amplitude and phase modulation method results in the simultaneous transmission of K1 plus K2 is equal to log base 2 M1 M2 binary digits occurring at a symbol rate RB over K1 plus K2. Now you see the difference. Previously we have K is equal to log to M. Now we have K1 plus K2 equal to log to M1 M2 binary digits. So figure 7.22 illustrate the functional block diagram of QAM modulator. So the objective is to transmit a QAM signal given this binary data. So the first step is to serial to parallel conversion. So bit sequence are coming serially 0001. Then we convert them into parallel combination of bits. Then transmitting filter GT. This is a shaping filter GT or pulse shaping filter. Pulse shaping. Then we have this balance modulator, product modulator or some variant. We have two carriers, cosine 2 pi FCT and sine 2 pi FCT. So this oscillator is generating this carrier. So one carrier goes to this one and the other signal is coming. So AM S into GT and then we have this product modulation. Then from this side we are getting sine function. So they are both added together and we get the corresponding QAM signal, this one. This one or this one, both are same. Okay, so you can get this, you can compact it and put it in the amplitude phase form, section equation 21. So this is the amplitude and phase form. So sine and cosine can be grouped together into a single cosine. So this equation, actually equation number 20 is implemented here. This equation 20 is implemented here in this diagram. So this is the functional diagram of the modulator, which is QAM modulator or QAM transmitter. If we add RF over here after this, then we get the QAM signal. So it is clear that the geometric signal representation of signals given by equation 20 and 21 in terms of two-dimensional signal vectors is this expression. So this, how to get the signal constellation using this expression. For any point you can put the value of AMC or AMS. So you can construct a signal space constellation for QAM. So this is the example of 64 QAM. This first four. If we take this one, this is m equal to 4, then we have m equal to 8, then this whole thing is m equal to 16, then m32, m64. So you should be able to construct these constellation diagrams. So these are the corresponding examples of combined PAM or PSK signal space constellation diagram. Again, we have to find the Euclidean distance between any 2 points, and this will affect the error performance of the receiver. So we have now covered section 7.3. Section 7.3, if we look at our syllabus for midterm, now we have almost covered this chapter of 5th edition, basic digital modulation schemes. Okay, so we are quickly moving toward the optimum receiver design for AWGN. Chapter 1, chapter 2, then this is the section 7.3. So now we have basic knowledge of modulation scheme, we can quickly go through this section, and then we can move towards the optimum receiver design for digitally modulated signals in additive wide Gaussian noise channels. Okay, so let me show you some slides, corresponding slides for section 7.3. So we are now quickly summarizing it. Representation of digitally modulated signals. So digital modulation or digital signal is nothing but mapping the bits to waveform. Serial to parallel conversion, we have parallel k bits, and then we select different waveforms, signals. Examples are actually these slides are from the 5th edition. So Proctor says consider memory less or memory with memory modulation schemes. Uh, so this pulse amplitude modulation is memory less modulation scheme. Similarly, phase shift keying, quadrature amplitude modulation scheme, multi-dimensional modulation, frequency shift keying. These are a memory-less modulations. So they are not dependent on the previous sequence of the bits. But if we get modulation scheme with memory, then we have differential phase shift keying, or then another division is either linear or non-linear. Linear modulation with memory or non-linear modulation with memory. So differential phase or continuous phase shift keying. So these are some of the advanced techniques we will not cover in this course because of the time budget. So if we know the basic scheme, PAM, PSK, and QAM, we are good enough. Similarly, frequency shift keying, I have covered this in my previous lecture. So you got sufficient idea now of different. So these are some of the schemes which are used in modern wireless systems. So all these slides are actually summarizing the same thing. PAM, band pass PAM, ठीक है. उसके बाद symbol rate, bit interval. You should be able to know these expressions. Band pass PAM is also called amplitude shifting. Okay. So don't confuse yourself. What is PAM? What is ASK? They are nothing but same thing. Band pass PAM is also called amplitude shifting. ASK. Signal energy, how to find the energy in the baseband PAM and then energy in the band pass PAM. Signal space representation is the same thing as finding the orthogonal basis function and for baseband PAM and then band pass PAM. These expressions, you should get the concept of these expressions. Otherwise, it would be difficult for you to have good marks in your quizzes or in the midterm or final. So constellation diagram for PAM, 2 PAM, 4 PAM, and this is 8 PAM. Euclidean distance, finding the Euclidean distance, then doing this example. So this is amplitude modulated signal and baseband PAM, and then it's band pass version. So what is the difference between baseband and band pass? We simply multiply it with the carrier. SM is equal to AM times PT, or in our previous discussion it was GT. PT or GT are same thing. Pulse shaping function. Then we multiply it with the carrier. Okay. Time with M is equal to 2. Then phase shift keying. So Proctis has given a different notation over here, but if you look at this, it is same thing. So cosine 2 pi FCT and minus sine 2 pi FCT, then GT into this thing was actually our AMC. AMC or GT into this sine phi M was our ACM. in our previous discussion. So this is the phase which is being changed in case of PSK waveforms. So complex baseband representation can also be used in terms of exponentials. You know, exponentials are nothing but sine and cosine components. So GT is rotated by this phase, complex baseband. So this is a baseband signal. If we multiply this with carrier, then it will become band pass representation. So we can also find the signal energy in the baseband, signal energy in the pass band. Then signal representation is the geometric representation. So now you see that this signal is a two-dimensional signal because we have two basis functions, phi 1 and phi 2. And these scalars are represented over here. So these are the constellation points. Okay. So this is the phase modulation, PSK. M array PSK, 2 PSK, 4 PSK, 8 PSK, or octal PSK. I will share all these slides with you. Then the Euclidean distance, minimum Euclidean distance. The next scheme is quadrature amplitude modulation. Quantum waveforms. You can see that we are using two carriers, quadrature carriers, sine and cosine. AMI is AMI plus AMQ, in phase component and quadrature component. So these are the different ways of representing waveforms. So determine whichever is good for you. Either you understand this one or the chapter 7, complex baseband. Then signal energy, signal space representation is two-dimensional, phi 1 and phi 2. In this case, AMI. This is the first coordinate. This is the second coordinate. And then we have Euclidean distance, signal space representations, m equal to 8, n equal to 16. Then we have 64, QAM, rectangular QAM. Okay. So we have covered up to this point. Now I will stop this and I will share this video with you. Previously I shared 4 videos because the size of video was restricted by YouTube, so I split it into 4 parts and I have shared the links. Similarly, for this video I will also do the same thing and I will send you multiple links for this lecture, which is for lecture 6. Since in our lecture 6 today we will be conducting a quiz at 8 p.m. so you should be ready for the quiz 1 at 8 p.m. and you will be given 45 minutes to solve that quiz. So I would recommend that you should be able to send me your PDF files of your solution of quiz 1 using your email address or using your official email ID. Don't send it from Gmail or Yahoo addresses. So now we are ready to move towards section 7.3 and 7.4, the optimum receiver design. I will also record the videos for those the receiver, optimum receiver, because it is very important topic and the core of our digital communication course, how to design optimum receivers. Okay, I will stop it over here in this session, which is now on March 25th, 2020. Okay.